Hey everyone, I'm about 9 videos into this right now. I don't know about you guys, but there's been a lot of retakes and takes and takes, and I'm getting a little frazzled. But I want to talk to you about electromagnetic radiation. You know of it as light, but an electromagnetic wave is well beyond just the visible spectrum. In fact, the visible spectrum of light is actually really small compared to the entire range of electromagnetic radiation. Electromagnetic radiation has two root words, electro as in electrical, and magnetic as in magnet. An electromagnetic wave consists of two fields, an E field and a B field, both perpendicular to each other and perpendicular to the direction of travel. The E field is the electrical field, and the B field is the magnetic field. The E field is a region around a charged particle or object within which a force would be exerted on another charged particle or object. So I'm going to draw that. So I have my charged particle here in the center. I'm going to give it a positive charge. And the E field is going to leave that charged particle normal to the surface, or along the normal, like that. And it is going to go on pretty much for infinity. Now, the strength of the E field is going to be directly related to how close all these lines are to each other. So if I'm really close to the center or to the surface of this particle, these lines are close together. But as I get further and further away and I see these lines, they start to separate. I have this big distance between them, right? Now, if they're further away, the strength is less. So what we can see here is that the strength of this field is directly related, there we go, directly related to how close these lines are and basically how intense the flux is at a certain point. So how do I calculate the flux? Well, Gauss's law gives us a method of measuring the E field in both its flux density but also in the strength of the field, and if you go so far as to find out to calculate, you can find the vector of that field as well. So Gauss's law looks like this. So it's proportional to the quantity of the charge contained within a closed surface. Now this surface, we say surface, but really it's a volume, but it's the skin of that volume around this area. So what we would do is we would find our charge and we would draw a Gaussian sphere around the charge, and from here we'd figure out how much charge is located inside of it, whether it's just one little guy or 4 guys or what, and then we would run the math and determine how strong the field is inside the sphere. To do so, we would need to know the radius of the sphere so that we could calculate what the area of that sphere is on here. Now, what's really interesting about Gauss's law is that it doesn't really matter the shape. The law is always true. Now, as far as doing the calculation, the shape is really important, because if the shape is really wonky, you have a really fun time trying to figure out what the area is. So in all cases using Gauss's law, you want to make sure you use a shape that is conducive to easy mathematics, right? And we all love that, especially me, because I suck at calculus. So if I do something as simple as a sphere, then I don't have to do any integrals, and that's freaking wonderful. Okay. So here we have a graph that shows the electric field strength in relation to the distance from the center of our Gaussian sphere. Now, as you can see, as we move away from the center, the field strength increases. Now, that's because as we move outward, we're gathering up more and more of these charges that we see here. And then once we get to the surface and all our charges are enclosed, then the strength falls off like 1 over r squared. Now with one charge, it's quite simple. It's just strictly kq over r squared r hat. Now this is k right here. And that's a pretty simple one to do. You would just find your point where your charge is. You place your test charge at a distance from that. You determine what that distance is, and then you plug that into the equation here. Oh, that's not good. Okay, so Gauss's law tells us the field strength. What about that force? It says that the region around a charged particle or object within which a force would be exerted on another charged particle. Well, that's what Coulomb's law is for. Coulomb's law tells us the force. And if you look at Coulomb's law here, you have KQ over R squared R hat, which we recall was also E. So now we're taking our E field and we're adding in a charge to it, and it's producing a force. Interesting side note, Coulomb's law looks an awful lot like the gravitational force. You can look at this and just see KQQ over R squared R hat. If you have a bunch of fields already calculated, you can simply add those fields up using vector addition. The same thing goes for the forces. If you want to, or you decided to, you could have all your fields calculated to a certain point and then place your charge there. And you could do each one individually and create a force from all the different points and then add the vectors of those forces together. Or you can take the fields, add them together to get the field at that point, and then add your test charge. Both methods are completely viable, and it really depends on what data you have and what data you don't have. Now you may just say to yourself, oh wow, gee, that's great, E field. So what? What does it mean? Well, the cool thing is with an E field is you can use those calculations to figure out how certain electrical components work, or even with those calculations figure out how to make electrical components to do something that you need. One of those things is a capacitor. A capacitor works strictly by the amount of charge that's deposited onto plates and the way the E fields interact. Here we have the depiction of a capacitor. And here we can see that the capacitance is the ratio of the change in electric charge of a system to the corresponding change in its electric potential. And here we have the charge, and here we have the change in its electric potential for capacitance. Now, capacitance isn't something I want to go into much today because we're on a very limited time schedule, and I want to get over to the other field, the other component of light, the magnetic field, or the B field. So my favorite thing is the magnetic field. I like the magnetic field because I get to do stuff with it. I can see it really easily. I can see it just in a magnet. I can see it with an electromagnet, or the way a solenoid operates. Motors and generators all use magnetic fields, and so I get to really see those, interact with those a lot, and they've always made more sense to me. You can throw iron filings down on a sheet of paper or a table and put a magnet under there, and you can watch the way the filings orient themselves to create the shapes that show you the field lines of a magnetic field. And magnetic fields are definitely a lot of fun to play with and make stuff with, and so I really like the magnetic field. But what's interesting about a magnetic field is that the field lines don't travel along the normal like E field lines. Magnetic field lines travel parallel to the surface. So Gauss's law doesn't really do anything for us anymore. If we try the same technique as we tried with the E field, we're going to get zero. We're going to have a bunch of field lines that run parallel to our surface or move in the surface and then back out of the surface again, or vice versa, and the net is going to be zero. So we know that a magnetic field through a closed surface is zero. Okay, well that's data, I suppose, but we can't do a whole lot with it using Gauss's law. But that's where Ampere's law comes in. Ampere's law tells us how that magnetic field is produced. You can look at it and see already that it has the components in it that define how you produce a magnetic field. If I pass current through a conductor, then I'm going to get a field. So if I have a conductor and I pass current through it, then it's going to generate a field. it's going to be in accordance with the right-hand rule, where you grab the conductor, you put your thumb in the direction of the current flow, and your fingers wrap around the conductor, and it tells you what direction the field lines are going to go. Excuse me. But what's really cool is you can look right at Ampere's law and see current and length. Right? You can get an idea of what the field is going to be like based on the actual parts that are generating the field. Here's an example right here of how you would find the magnetic field inside a wire, or outside of the wire. Now luckily for wires, if the current density is linear, then the calculation is really, really easy. It's just some simple algebra. But if you start getting variable current densities in the wire, then the math can get a little trickier. The field strength for other shapes is shown here. Now let's go back to the E field really quick. If I have two particles and they are of opposite polarity, I already showed earlier that there's a force that could be created, opposite or similar polarity, and the force will be proportional to their charge and the distance between them. Now, if the polarity is the same, and the force is going to be a separative force, going to push them apart, and the polarity is opposite, they're going to be attracted towards each other. Now, this also works if I have just a uniform E field that's traveling in one direction. If I had a uniform field and it was traveling in this direction, and I put my charged particle in it, and it was a positive, then it's going to want to move in this direction. But what about a magnetic field? Well, a magnetic field is different. If a magnetic field is here, and it was traveling in this direction, then I added a charge to it. I would have to use the right-hand rule to figure out what direction that charge is going to go. And if the charge was, say, moving like this, and it was a positive charge, then I would use my right-hand rule, and I would determine that the charge is going to move into the board. So now hold on a second. If I have a magnetic field and an E field together, well, they work perpendicularly. And then I add a charge to them, what's the final result going to be? What's my force going to be? What's the direction going to be? Well, that's where Lorentz Force comes in. So the Lorentz Force is basically a depiction of what I drew on the other tab there. We have the force by the B field on a moving charge. There's a velocity of the charge. There's a charge value itself. And then we have the force of the particle and the E field. So this is going to be a force, and this is going to be a force. And then we're going to add those forces together, and that's just going to be two vectors. And we're going to get a final vector, and then we're going to have a resultant force. Alright, so we've taken the E field, and we've taken the B field, and we've combined them to get a force, but they also come combined as light. What I find really interesting about light is that C is equal to E over B. Now, C is already a very large number, 3.0 times 10 to the 8th meters per second. And so the E must be much, much stronger than the B. Just a little something to think about. Alright, so we've taken E fields and we've taken B fields and we've put them together, we've created light, we've added a particle to it and got Lorentz Force. Last thing I want to talk about is Faraday's law. Faraday's law is really cool because it covers induction, and induction to me, or inductance, is also really interesting because that's where that magnetic field gets to do stuff, right? If I take a magnetic field and it's just sitting on my desk, it's not doing anything, it's just sitting there. But if I take a conductor and I pass it by that magnetic field or through the magnetic field, I can get myself a voltage. I can induce a voltage. That's how a generator works. I can also do something different where I can have two coils next to each other and I can energize it and then de-energize it, and a field will be produced and it'll expand and then it'll shrink again, and that field is crossing those the coils on the secondary conductor, and that generates a voltage as well. So I can either move the field into and away from a conductor, physically do it, or I can expand and contract the field by changing the voltage in it. And so both those ways, I'm producing a relative motion between a conductor and the field. And what's really cool is I can look right into Faraday's law, and I can see that happening in the equation. I have this guy, which is the change of the field with respect to time. So that's going to give us the relative motion aspect of that. And then I have the number of coils, and that's going to give us how much or how many coils are there to actually interface with that moving magnetic field to give us our potential. All right, so I'm out of time. If you're still awake, hopefully I maybe put some things together that you may have missed. Considering that this is our finals week, I doubt it because you're all doing the same thing. But if you're someone who's not in my class and you're seeing this video, maybe I put some pieces together for you, and I hope that's what happened. And if you did fall asleep, I hope your nap was really good. And I'm just excited for the semester to be over and for this lockdown to end because I really want to get a freaking haircut. I don't know about you guys. I want a haircut. Thanks for watching.